The current divider is the equivalent of the voltage divider but for currents. With the voltage divider, we had a large voltage and we divided it using resistors. Here we have a large current and we divide it in different branches using resistors as well. The simplest form of the current divider is shown on the left. And it's made by two resistors in parallel. The voltage divider is in parallel to a voltage source, a battery in this case, and we have called the overall current from the battery IBAT. The Kirchhoff current law tells us that IBAT will have to split between the two branches of the two resistors. We can call I1 the current in the resistor R1 and I2 the current in the resistor R2. The goal of this lesson is to determine the value of I1 and I2 relative to IBAT. In other words, we want to determine how the current IBAT divides between the two nets of the circuit. R1 and R2 are in parallel, and we know the value of the voltage across them, VBAT. Therefore, it's natural to start by calculating the value of the current I1 and I2. The current I1 is simply equal to VBAT divided by R1 and I2 is equal to VBAT divided by R2. IBAT is also easy to calculate as it is the current going into the parallel between R1 and R2. I use this symbol to indicate the parallel between R1 and R2. The parallel between R1 and R2 is equal to R1 by R2 divided by R1 plus R2. Now, if we combine these two equations into one, we obtain that IBAT is equal to VBAT multiplied by R1 plus R2 divided R1 multiplied by R2. Finally, we can calculate the ratio between I1 and IBAT and I2 and IBAT, which give us the percentage of the current IBAT going into R1 and the percentage going into R2. Needless to say that a similar approach can be used to find the value of the current in voltage dividers with more than two branches. These equations that we have just calculated are similar to the one of the voltage divider, but there is a fundamental difference. If we had a voltage divider composed by two resistors, R1 and R2, and we wanted to calculate the percentage of VBAT falling on R1, the results would have been R1 over R1 plus R2. In the case of the current divider, instead, the portion of IBAT going into R1 is R2 divided by R1 plus R2. You see the difference? In the case of the voltage, we put in the numerator the resistor whose voltage drop we are calculating, while in the case of the current, we put the other resistor. You see here we are calculating I1 over IBAT, and the result is R2 divided by the sum of the resistor. And at the same time, when we want to calculate the current in I2, we have R1 divided by the sum of the resistor. This is the opposite of what you get if you are calculating the voltage over this resistor in a voltage divider. This might seem strange, but it's very intuitive. In the voltage divider, for the same current, a high resistor takes a larger portion of the input voltage, while in the case of the current divider, for the same voltage, the higher the other resistor, the higher is the portion of the current that will prefer to flow in the resistor under study. Current dividers work well when their different branches are truly in parallel with each other. If you were to connect anything in series to any of the resistors, like this little box in series to R2, the equations of the current divider that we have just calculated won't be mathematically correct anymore. But it will still be okay as long as the voltage drop across this new element is much smaller than V bar.